So welcome to this online lecture for solutions. This is the part that won't be covered in class. Much of this will be covered in your lab, and also most of this should be a review from Chem 1A and from your high school courses on solutions and different concentrations, but it's always good to have a nice review. Just to go over a couple of points from these slides. Your Chem 1B instructor will cover this section in lab, and if your instructor isn't there or if you missed something, you can watch this video. Also, this concept from these slides will be put into practice by doing Study Guide B. So remember, all of this work that you do on Study Guide B is fair game for lecture and for lab, for your quizzes and for your tests. So make sure you understand what's going on. And also, as you do Study Guides A and B and anything within the lab course, make sure you have no magic answers. And what I mean by magic answers are questions that require some calculations. So I want to make sure you show your work rather than just a magical number appearing on the page without showing where that number came from. So make sure you always show your work for your calculations and how you set up the calculations, so that I know that you understand what's going on and you just didn't copy that number from your neighbor. So as we look at concentrations, solutions have variable compositions. You can have different amounts of your solute within your solvent. And to describe a solution, you need to describe the components of it and the relative amount. So what's in it and how much is there. What's in it and how much is it there. So that's why concentrations are important. And when we use the terms dilute and concentrated, those are very qualitative terms. And so it's nice to have more quantitative descriptions of those concentrations. And a concentration is the amount of solute in a given amount of solution. So make sure you remember those terms. So your solute and your solution, and let's see, we don't have solvent here, but the concentration is the amount of solute in a given amount of solution. So we'd see something like this, especially for like molarity. But occasionally the amount of solute is given per amount of solvent, and we'll see this when we talk about molality. So those are just some examples where those definitions of your concentration differ slightly. So our first one that we want to talk about is molarity. So molarity is the moles of solute per liter of solution. And this is used because it describes how many molecules of solute are in each liter of solution. And this is a very common unit of concentration that chemists use. So for example, if a sugar solution contains 2 molar, it has 1 liter of solution and contains 2 moles of sugar. Now let's say we have twice that volume, we have 2 liters. Well, that 2 liters is going to have 4 moles, but the ratio is always the same. So 4 to 2, 2 to 1, if we reduce that ratio, it's still a 1 to 2 ratio. And to describe that mathematically, we can say that molarity is the moles of solute over liters of solution. Now notice when we use the abbreviation for molarity, that's a big capital M. And it's going to be very important for distinguishing between molarity, which is big capital M, and molality, which is small capital M. And when you're doing it by hand, it can be difficult to distinguish between the two units. So you need to be very careful when writing your big capital M for molarity and your small capital and your small m for molality. So molarity and dissociation. The molarity of an ionic compound allows you to determine the molarity of dissolved ions. So remember when we talk about ionic compounds, so like this calcium chloride, when it dissolves into solution, it breaks up into its ions. And so you have a calcium, so a calcium 2+ ion, your cation, and 2 chloride anions. So you're going to have a total of 3 ions in solution for every 1 calcium chloride. Now, if we look at this, the 1 molar calcium chloride solution, when dissolved, will give you, let's see, make sure I'm reading this correctly. See, 1 molar of calcium chloride contains 1 moles of calcium chloride in each solution. So again, very basic definition. But because the calcium chloride dissociates into 1 calcium 2 plus ion, the molarity of the calcium 2 plus in solution is also 1 molar. Because notice it's a 1, let me change my pen, because it is a 1 to 1 mole ratio. So when the calcium chloride dissociates to give 1 mole, it's also going to be 1 molar of calcium 2 plus. But when the calcium chloride dissolves and you get the chloride ions, that is a 1 to 2 mole ratio. So when the calcium chloride dissociates, it gives you 2 chloride anions, and so the chloride anion is 2 molar. It's going to be twice that of the calcium chloride. So you have to take into account that factor. So here's that other unit of concentration, the molality. So remember we said on the previous slide that molality was lowercase m, and this is the moles of solute per kilogram of solvent. So it's defined in terms of the solvent, not the solution like many other concentrations. But the nice thing about molality is that it does not vary with temperature because it's based on the masses and not the volumes. So for instance, if you make a 1 molar sugar solution and you put it in the refrigerator and you have a volumetric flask, if you go and after the solution's chilled, you'll notice that the water volume is lowered even though none of the solution was taken out. But the molality would be the same because you still got the same mass. So remember, solutions will change their volume based upon the temperature, so you can have varying molarities, but the molality will not change. So that's why some people prefer the unit of molality, especially for analytical purposes. Now another unit of concentration is the percent. So it's the parts of solute in every 100 parts of solution. So the mass percent is by mass. So mass of solute in 100 parts of solution by mass. For example, if a solution is 0.9% by mass, then there are 0.9 grams of solute in every 100 grams of solution. Or another way is to look at it as 0.9 kilograms of solute in every 100 kilograms of solution. So the mass percent is the mass of solute in grams over the mass of solution in grams. And notice that the grams will cancel out, so that's why you could use kilograms and kilograms, as long as those mass units cancel out, times 100%. Now remember, the mass of the solution, and you'll need this for some of your calculations in your 1B study guide, your mass of your solution is the mass of the solute plus the mass of the solvent, and that will give you your mass of your solution. So again, looking at percent concentration, percent is just the part over the whole times 100%. Mass percent is the mass of solute per mass of solution times 100%. And then sometimes you do the mass, percent mass by volume. So that's the mass of your solute in grams over the volume of the solution in mils times 100. And in this case, the mass of the solute plus the volume of the solute don't equal the volume of the solution. So you have to be very careful. You can't just add the mass of the solute and the volume of the solvent and get the volume of the solution, because those do not equal. And then there's also volume percent, which is the volume of solute over the volume of solution. And you've got both of those in units of mils, so those will cancel each other out, times 100%. And the volume of the solute plus the volume of the solvent doesn't necessarily equal the volume of solution. So volumes are not always additive with solutions. You have to be very careful of that. Now I want to talk about using concentrations as conversion factors. So concentrations show the relationship between the amount of solute and the amount of solvent. So if we have a 12% mass by mass sugar aqueous solution, that means that you have 12 grams of sugar in 100 grams of solution. And when we have these triple arrow bars like this, this means exactly or by definition. So it's similar to the equal sign, but it has a little bit more meaning. Or another way to look at this is 12 kilograms of sugar equals or is in 100 kilograms of solution, or 12 pounds in 100 pounds of solution. So you can use various units of mass as long as you still have that same ratio. Now, a 5.5% mass by volume silver in mercury means that there are 5.5 grams of silver in 100 mils of solution. So that volume means the volume of the solution, and the M means the mass of the solute, so the mass of the silver. Now, a 22% volume by volume alcohol in aqueous solution means that there are 22 mils of ethanol in 100 mils of solution. And the concentration can then be used to convert between the amount of solute into the amount of solution, or vice versa. So you can go back and forth by using the description of the concentration as conversion factors. Now, this video is actually online on Blackboard already, so rather than embedding it within this video, I'm not going to do that. Now, when you watch this video online on Blackboard, a couple of things that you should notice is that when they read the volume, the volume is to the meniscus, so the bottom of the meniscus should reach this line. But some important parts, you add your solvent, you add your solute and some of your solvent to get your compound to dissolve, so you can swirl it around, because you can't add a magnetic stir bar or anything like that, because that'll change the volume. So you add your solid in there, or your solute in there, and you add some of your solvent just enough so you can begin to dissolve it to make your solution. And then once you get it completely dissolved, wash any remaining material down the neck of the flask and dilute up to the mark, so that the meniscus is just, the bottom of the meniscus is at the line on the volumetric flask. And remember, you always read the meniscus at eye level. So some things you should take into account when preparing a solution. You need to know the amount of solution and the concentration of the solution. So you need to calculate the mass of the solute that you need. And so you start with the amount of the solution, and you use the conversion, use the concentration as a conversion factor. Oops. So let's say we want a 5% by mass. So that means that we want a 5 grams of solute per 100 grams of solution. So dissolve the grams of solute in enough solvent to total the amount of solution. For example, how would you prepare a 250 grams of a 5% by mass glucose solution? So we're given that we have we want to prepare 250 grams of the solution, but we want to find the mass of the solution that needs to go into it. And our concentration that we want is a 5% by mass, so that means we need 5 grams of glucose for every 100 grams of solution. So we basically want to take our grams of solution and get to the grams of glucose. And by using the concentration, we can make that conversion. So we're going to apply our solution map. So we start off with our 250 grams, and then we use our concentration. So 5 grams of glucose per every 100 grams of solution, because remember, that came from the concentration. So grams of solution cancel out, and grams of solution cancel out. That leaves us with units of glucose. So 250 times 5 divided by 100 gives us 12.5 grams of glucose. So to make this solution, we dissolve 12.5 grams of that glucose, and we're going to put it in a flask, and we're going to add enough water and put it on a scale so that the total mass is 250 grams. So we'll add water until the total mass is 250 grams. Now I want to take a look at solution concentration in parts per million. So solution concentration using ppm, or parts parts per million. This is the grams of solute per 1 million grams of solution. Or another way of looking at this is milligrams of solute per 1 kilogram of solution. So we've still got the same ratio. Or 1 liter of water per 1 kilogram of water. So for water solutions, we often approximate the kilogram of solution as the kilogram or 1 liter of water, basically because 1 ml of water equals 1 gram at room temperature. So we often make that approximation to make math easier. So parts per million, we can use the grams of solute per the grams of solution and multiply that by 10 to the 6th power. So again, we said we can look at like this, or the milligrams of solute per kilogram of solution, or milligram of solute per liter of solution. These are all ways to get at parts per million. So what volume, we're going to look at example 12.3, what volume of a 10.5% mass soda solution contains 78.5 grams of water, and they give you the solution density of 1.04 grams per mil. So you know that you've got 78.5 grams of sugar. You want to find the volume. So our idea is to take the grams of solute, then find the grams of solution, then find the milliliters of solution. And some of the relationships that we can use is 100 grams of solution equals 10.5 grams of sugar. So we get that from our concentration. Or another way of looking at that, 1 ml of solution equals 1.04 grams. Oh, sorry, that's the density. 1 ml of solution equals 1.04 grams. So if we start from our gram of solute, use our concentration, we can convert to grams of solution. And then once we have our grams of solution, we can then use the density to get the mils of solution. So that's our plan of attack. So we're starting off with our 78.5 grams of sugar, multiplying it by the concentration, where the 78.5 grams of sugar is in the denominator. So those grams of sugar, the grams of sugar cancel out. So now we're in grams of solution. So we take that grams of solution, multiply it by the inverse of the density. So we want to do that so that the grams cancel out. Now we're in the volume of the solution, which is in mils. And so we get an answer of 719 mils. Showing where all the units cancel out, so we get the appropriate volume. So the units are correct and the magnitude seems reasonable. And so we can feel confident that we answered this question correctly. Now another unit of concentration is the mole fraction. So I need to know the mole fraction for some of our other calculations in chapter 12. And the mole fraction is just simply the fraction of moles of one component in the total moles of all the components of the solution. And the total of all mole fractions in a solution have to equal 1. So you can't have a number larger than 1 when you add up all the parts. Because remember, we're looking at the unit as 1, and we're looking at the individual components of them, and they can't add up to be more than 1. And since it is a fraction, that fraction is unitless. Now the mole percentage is the percentage of moles of one component in the total moles of the components of the solution. So it's just simply the mole fraction times 100%. And the mole fraction of A, so if we've got a compound A, we have the big X represents mole fraction, and the little a subscript represents what component of the whole we're looking at. So if we're looking what that means the moles of components A over the total moles of solution. That would be our mole fraction of A. Now here's example 12.4a. It's asking what's the molarity of a solution prepared by mixing 17.2 grams of this organic compound with 0.5 kilograms of water to make 515 mils of solution. So you're giving the mass of your compound, the mass of your water, and the volume of the solution, and we want to find the molarity. So if we have the mass of the compound, we can get to the moles. We can do that by using the molar mass of the compound. And if we have the mils of the solution, we can convert to liters of solution just simply because there's 1,000 mils in 1 liter. And then, so once we have the moles of the compound over the volume of the compound, then we can get the molarity. And so those relationships will help in those conversion factors. So as we set it up to solve it, we have 17.2 grams of the organic compound. The molar mass is 62.07 grams per mole, so you need to calculate that from the molecular formula. And so that would give us 0.2771 moles of our solute. And we're just using that underline underneath the 7 just to show, keep up with our sig figs, but we're keeping more digits than we need just so that we don't introduce rounding errors. But because we've got 3 sig figs here, 4 sig figs here, we should have 3 sig figs in our final answer. So this underline under this 7 tells me anything after that 7 I'm going to need to get rid of later, because I should have 3 significant figures. So now that I've got the moles, because those grams cancel out, I can then take the volume of the solution, that 515 mils, and convert that to liters. So mils will cancel out. Now I take my moles, divide it by my liters, and mathematically I get 0.538. And so I've rounded so that I only have 3 significant figures. So I have 3 sig figs here, 3 sig figs here, so I should have 3 sig figs in my final answer. Okay, so now it's 12.4b. Rather than asking for molarity, now we're looking at the molality. So what is the molality of a solution prepared by mixing 17.2 grams with 0.5 kilograms of water to make up 515 mils of solution? So be very careful when you're reading these questions to make sure you don't accidentally misread molarity or molality. So again, we're given the mass of the solute, the mass of the solvent, and the volume of the solution, and we want to find the molality, which is little m. So we're going to start off with the grams of our solute converted into moles using the molar mass. We've got the mass of our solvent, which is given, and if we divide those two, we should get the molality. Because remember, molality is moles of solute per kilogram of solvent, and then the molar mass, which we calculate from the formula, is 62.07 grams per mole. So it's 17.2 grams of the solute, and you're going to divide it by the molar mass. That'll give you your number of moles, so the grams will cancel out. And again, you've still got 3 sig figs for the moles, but we're just keeping that extra 1 so we don't introduce rounding error as we do more calculations with it. So we then, to get the molality, we take the moles of the solute, which we just now found, divide that by the mass of the solvent in kilograms, so 0.5 kilograms of water, and our molality is 0.554 molal, and that big M should be a lowercase m. So a little typo there on my part. So the unit is correct and the magnitude is reasonable, so we can feel confident that we answered that question correctly. Now going on to C, still the same sets of conditions, just different units of concentration. So this time they're asking for what's the percent by mass of solution. So we're given the same thing, but now we want to find the percent by mass. So what we're going to do is take the grams of the solvent and then find the grams of solution, and then using the grams of the solute to get the percent. And to do some of these conversions, we're going to need to know that there are 1,000 grams in 1 kilogram. Because remember, our percent by mass is the grams of solute per grams of solution times 100%. So we've got 0.5 kilograms of water. And we're going to convert that to grams of water just by using their 1,000 grams per kilogram. So those kilograms cancel out, we're in units of gram. And we're going to add our mass of our solvent, so that 500 grams of water, and the mass of the solute, so that's 17.2 grams of our solute. So we add the mass of the solute plus the solvent to get the mass of the solution. And notice that we are only significant to the ones place in this number. We are significant out to the tenths decimal place. So when we add these two numbers together, we can only be significant to the ones place. We can't be any more accurate than the ones place, so anything after the decimal would not be significant. So in this case we have 3 sig figs, but we're keeping the 0.2 just for now so that we don't have rounding errors. So to get the percent by mass, we take the mass of our solute, the 17.2 grams, divided by the mass of our solution, multiply it by 100%, and we get 3.33%. Now, again, same set of conditions, just different concentrations, so the mole fraction. So a lot of good examples on how to do these different concentrations. If they want to know the mole fraction of the solution, still given the same amount, we want to find X, which is the mole fraction. We take the mass of our solute, use the formula weight to get to the moles. We take the mass of our water, use the formula weight of water to get the moles of water, and we can use those to calculate the mole fraction. Remember, the mole fraction will be the moles of our solute per the moles of total of everything. And we're going to use the molar mass of our solute, still 62.07 grams per mole, and the molar mass of water is 18.02 grams per mole. And the mole, there's our mole fraction definition. So again, calculation of the moles of the solute. The grams will cancel out. And here's our calculation for the moles of water. We take our mass of the water, which is 0.5 kilograms, convert from kilograms to grams, so the kilograms will cancel out. Now that we're in units of grams of water, we take the molar mass, divide that by the molar mass, so that 18.02 grams per mole. Grams will cancel out, and that'll give us moles of water. So the kilograms cancel out, the grams of water cancel out. Now we've got moles of water. Now, to get our mole fraction, we take the moles of our solute, that 0.2771, divided by our total moles of everything. So we have to add that 0.2771 moles of solute plus the moles of our solvent to get our total moles. And so that's what we've done here. So this is the moles of our solute over the total moles, so that's the moles of our solute plus the moles of our solvent. And so our mole fraction is 9.89 times 10 to the minus third. And again, remember that mole fraction is unitless. Okay, another example using similar conditions, but now we're looking at the mole percent of a solution. Given the same amount, now we want to find the mole percent. So we do the same calculations before, but we're just going to multiply it by 100%. So the same calculations. So we've still got the moles of our solute, and then the moles of our water. The units cancel out. And if you're missing this and this goes too fast, remember you can always pause or rewind or anything like that, since it is recorded. So the same calculations before, the only difference now is that we multiplied it by 100% to get the mole percent. Now when you're converting concentration units, assume a convenient amount of solution. So when you're given a percent mass by mass, it makes your life a lot easier if you just assume that you have 100 grams of solution. So let's say you've got a 50% mass by mass solution. So for every 100 grams of solution, you've got 50 grams. So rather than assuming you've got some weird numbers, make your life easier just by assuming you've got 100 grams of solution. Same thing as if you've got a given percent mass by volume, so assume 100 mils of solution. So just by making these assumptions that we show here on this slide, it'll make your life a bit easier. Whoops. Also, determine the amount of solution in non-given units. So if assume amount of solution in grams, use density to convert to mils and then to liters. Or if assume the amount of solutions liter or mil, use density to convert to grams. Also, determine the amount of solute in this amount of solution in grams and moles. Also, determine the amount of solvent in this amount of solution in grams and moles, and use definitions to calculate other units. Now, doing these types of calculations over and over again, especially like you will with study guide B, you're going to start to see the patterns, and your brain is going to recognize what to do more quickly. But in the beginning, it's going to take a while, and so you need to just keep trying, keep working at it. And if the first time you try a problem and you're not getting the right direction, it's okay. Take out a piece of scratch paper, try something else. But if you're having trouble figuring out what to do, this concept map that's actually found in your book may help you figure out what to do. So let's say if you're talking about your solute and you're given the amount of moles and you want to find the mass, you can use a molar mass to convert between these. These are different ways that you can get to what you need. So this is just a concept map. But there's no good replacement for just good old plain practice. So remember, I've got office hours. You can email me. There's tutors in the chemistry department office. But make sure that you're very comfortable with these types of calculations. And because you won't be using them just for Chem 1B, you'll be using those for other courses. And even I hear from some of the biology professors, understanding these units of concentration, are also important for them. So it's not just for us chemists that we need these, it's for many different fields. So good luck, and I hope this is helpful.